Hi everyone, my name is Adarsh, and this is my Physics 2211 Lab 2. So here's a table of contents. We have the introduction, the physics concepts, modeling, followed by the experiment, data analysis, and discussion, and lastly the conclusion. Introduction. The purpose of this lab is to analyze the motion of a falling object and how gravity and drag affect the motion and dynamics of the object. The models that we use are glow script models and tracker models, and the principles are Newton's second law, drag force, terminal velocity, and gravitational force. Lab preview and main result. So this video is just showing me dropping the paper ball, and the video shows an object's position as a function of time, and we can see how the object demonstrates the force of gravity and drag through the graphs. Physics concepts and modeling. So the main physics ideas in more depth: Newton's second law is F is equal to ma, where F is force, mass is m, and acceleration is a. And we have drag force, which is a resistive force that changes based on an object's speed. We have gravitational force, which is the force that between two masses that attract each other, and the gravitational constant for the universe is 6.67 times 10 to the power negative 11. Modeling. So we have the glow script model and we have the glow script graphs. And you can see we have the position versus time and velocity versus time, and I'll go more in depth into this on a later slide. Lab details. So the object I used was a crumpled paper ball, and this was so that the crumpled paper ball actually falls slower than other objects because the paper creates drag, and we can kind of see it affecting it. The observed position was using tracker, and the predicted position was using glow script. The angle that we used in the lab was calibrated based on the video. We recorded a meter stick and the same video and calibrated it used on that. Data analysis and discussion. So this is the experiment. So this is the experiment video. As you can see, it's just me dropping the same ball again. On the right hand side we have the graphs and the data. And all these red points are the point of mass at each frame. And a little more detailed graphs and data. So this is the table. It goes from time is equal to 0 to time is equal to 0.766. And as you can see, y is a bit more uniform and x is a little bit more ranky. So now for the code. We have two pieces of code. This is the glow script code for only gravity. So what I changed here was the ball mass, the ball position, and velocity right here, t and delta t. And in the while loop, we changed the fnet, and in the header of the while loop, and we updated the ball velocity and ball position. Now for gravity plus drag, everything is the same except for the proportionality constant, and this accounts for the drag force. So for the models, there are two models, the gravity model and the drag model, but you can see the difference in the data, and you can't see the difference in the actual photo itself because it's just showing the point of origin and the ball as it moves down. So I included this picture, and we have the position versus time graph and the velocity versus time graphs. The data for both of them are very similar, and the difference is very minimal, and I'll show you that in the next slide, which is this one. And as you can see in the graph on the right, we have the observed gravity plus drag and gravity, and you can only see two lines because the blue one, which is just gravity, is very hidden. So I include another graph which is gravity only, and it has predicted versus and observed. And so as you can see, the lines are very same. The data is different, but it's not, since it's a small distance and it's not a crazy mass or anything, the data is different in the decimals, and you can't exactly see that unless you zoom way in on these graphs. So the similarities and differences: both models account for gravity. Both models are based on the same principles. One model can show drag, and which is model 2, and it shows changes in acceleration due to drag. And model 1, the motion is consistent and the acceleration stays the same because of no drag. The similarities and differences between the predicted and observed are due to the possible sources of error, and they're on the next slide. So the sources of error are human error, which is like video recording, the angle, and then the tracker is not always exactly the point of mass because the quality is not perfect. The other factors, which are like other environmental factors that aren't taken into consideration in the calculations in the lab that we're doing today. Then we have the object and the assumption that we're making, and this can make the data kind of inaccurate. So some lab questions. What does it mean? The model that considers gravity and drag reaches terminal velocity, and gravity model does not. It only shows constant acceleration. What if the object was thrown downward? The object's terminal velocity will be reached quicker than if thrown from rest. And for the conclusion, the lab we examined is a motion of a falling object falling straight down. We watched the gravity and drag. We noticed that one reaches terminal velocity and one does not. It's just constant acceleration. Overall, the lab was fun to do and very educational because we used a lot of the principles that we're learning with, which is the foundations of physics. So we get to see it in action. And yeah, thank you.